Lesson 20-2, page 1021. A bag contains 12 red and 8 blue chips. The 2 chips are separately drawn at random from the bag. Suppose that a single chip is drawn at random from the bag. Find the probability that the chip is red and the probability that the chip is blue. Okay, so we want to find the probability of a red chip and the probability of a blue chip. So there are 12 chips that are red, and 12 and 20, 12 plus 8. So we got 12 over 20. Let's see, that would be 3 over 5. All right, blue, probability of blue, we have 8 blue chips in the bag, and we have a total of 20 chips. That's going to give us 2 over 5. 1b, suppose that the 2 chips are drawn separately, drawn at random from the bag, and that the first chip is returned to the bag before the second chip is drawn. Find the probability that the second chip drawn is blue, given the first chip drawn is red. So we're going to do probability that it's blue, given red the first one. Okay. So let's see here. Find the probability the second chip drawn is blue, given the first one is red. Well, let's see here. The first one was red, but we returned it. Okay, and there was a total of 8 blue chips. And since we put the 1 back, there's still a total of 20, and that's going to give you 2/5. Suppose that 2 chips are randomly separately drawn at random from the bag, and that the first chip is not returned to the bag before the second chip is drawn. Find the probability the second chip drawn is blue, given the first chip drawn was red. So again, we have the probability of blue given red. Okay, now this one here is something that's called independent. Okay, in other words, the second draw did not depend on the first draw. But this time here, since the first chip is not returned, that means that this one is going to be dependent or not independent, however you want to say it. So we only took out 1 chip, and it was red. So we had 8 chips, but we no longer have 20 in the bag. We have 19. Okay. In which situation the first chip is returned to the bag or not returned to the bag are the events that the first chip is red and the second chip is blue. That would be this one here. Okay. It's independent. It is independent when the events do not impact each other. All right, so here it was independent because it didn't matter, okay? Because you still had the full pot. Here it's dependent because you had now taken one of the chips out of the bag. Identify whether the events are independent or not independent. Flip a coin twice and get tails both times. That's going to be independent, okay? Because the first or the second flip does not depend on the first flip at all. Okay, it's two totally different flips. Roll a number cube and get 1 on the first roll and a 6 on the second. Again, independent, okay? Because it's still a 6-sided cube. So what each roll is independent of each other. Draw an ace from a shuffled deck, put the card back and reshuffle the deck, and then draw an 8. Independent, because on the second time, there were still 52 cards in there. There's 52 cards in the first, and there was 52 in the second. Rotate a bingo cage and draw the ball labeled B4. Set it aside, and then rotate the cage again and draw the label N38. Okay, these are not independent, okay, because we'll say there was 30 balls, and there's one N38. So on the first draw, they had a 1 in 30 chance. But on the second draw, it now becomes a 1 in 29. So it has a higher probability. The first ball had an effect on what could be, or what did or could be, the second. 3. Answer the question using the fact that the probability A given B equals probability A only when events A and B are independent. The two-way frequency table shows data for 80 randomly selected people who live in a metropolitan area. Is the event that a person prefers public transportation independent of the event that a person lives in the city? Well, let's see. All right, let's see here. What do we got? Probability and for prefers public transportation, the probability of T, and let's see, that's going to be 35 over 80. Now, the probability of T given C, that's the probability of T given C, prefers public transportation provided they live in the city. That's going to be 24 over 80. Okay, now the probability of T given C is not equal to the probability of T. So the events are not independent. The two-way frequency table shows data for 120 randomly selected people who take vacations. Is the event that a person prefers vacationing out of state independent of the event that a person is a woman? So what do we got here? Is the event that a person prefers vacationing. So we'll say probability of out of state and prefers out of state. That's going to be 72 over 120. 72 over 120. And let's see what that is. 72 divided 120. 0.6 equals 0.6. Now let's see the probability Out of state, given that they are a woman, out of state, given that they are a woman, well, that's going to be 24 over 40. 24 over 40. Well, that 24 over 40, is that the same as 72 over 120? Let's see. 24 divide 40. That's 0.6. 0.6. Okay. Since the probability of zero or out of state given that they're woman equals the probability of out of state, the two events are independent. A jar contains marbles of various colors as listed in the table. Suppose you randomly draw one marble from the jar. After you put that marble back in the jar, you randomly draw a second marble. So we're going to call this with replacement. Okay, we're going to call this with replacement. Use this information to answer the question, giving a probability as a percent and rounding to the nearest tenth of a percent when necessary. Okay, so let's take a look at number 5 here. What is the probability you draw a blue marble first and a red marble second? Okay. Since we're putting the marble back, we're going to do this with replacement. Which makes the two events independent. Two events are independent. So number 5, what is the probability that you draw a blue marble first and a red marble second? So the probability of blue, and let's see, that's 10. And how many are there total? I'm going to write total down here. Total 2018 plus 12, I believe, and plus 10. That's 60. So there's a total of 10 over 60. That's going to be 1/6. All right. Now, the probability red given blue. Okay. Well, since these are independent, that's actually going to be the same as the probability of red, which is going to be 20 over 60, or we'll say 1/3. So now our question is, what is the probability that you draw a blue marble first and a red marble second? So the probability of blue intersection red, that's going to be the same as the probability of blue times the probability of red. 1/6 times 1/3. And that's going to be 1 over 18. And I think we're supposed to turn that into 1 divided by 18. 0.056. 0.05. Are we supposed to go 3 places? All right. What about number 6? What is the probability that you draw a yellow marble first and a green marble second? So we have the probability of a yellow marble. And what is that? Yellow is 18 over 60. 18 divided by 60. 0.3. 0.3. Yellow marble first and the green marble. So the probability of green given yellow. Okay. And since we're putting the first marble back, that's the same as the probability of green. So let's see here. Green, there's 12. So we're going to have 12 divided by 60. At 0.2. 0.2. So the probability of yellow intersection green is going to be the same as the probability of yellow times the probability of green, which is, I can do fractions a lot easier than I can that. Let's see. That's the same as 3/10, and that's the same as 1/5. So I got 3 over 50. I can do it like this. Times 0.063 divided by 50. Yeah. Equals 0.06. What is the probability that you draw a yellow marble both times? Let's see. What is the probability you draw a yellow marble both times? Probability of yellow how many yellows are there? 18 over 60. We'll call this yellow 1. 18 over 60. And that was 0.3. And then we have the probability of yellow the second time, given we had yellow the first time. Again, since we put the first one back, there's still 18 yellow. So that's the probability of just yellow 2. And that's going to be 18 over 60. 0.3. What is the probability you draw a yellow both times? That's going to be probability of yellow 1 intersection, probability of, intersection yellow 2. Yellow the second time. So probability of yellow 1 times the probability of yellow 2. 0.3 times 0.3 I think that's 0.09. 0.3 times 0.3.09. All right, good. 8. What color marble for the first draw and what color marble for the second draw have the greatest probability of occurring together? Well, that would be the one with the most marbles in there. And that's going to be red. Red's got 20. Okay, so the probability of red, the first one, because look, I mean, 20. And since we're replacing them, it's still going to be. So 20 over 60, that's 1/3. And the probability of red second draw and red, given red on the first draw, since we're putting the first one back in, is going to be the same. That's 1/3. So the probability of red 2 times the probability of red 1, remember that intersection thing, probability R2 intersection R1 equals that right there, probability of R2 times probability of R1. 1/3 times 1/3 is 1/9. And let's see. That's it. Yeah. 1 divided by 3 times I said times is 0.11, which is 1 divide 9. Yeah. Or 0.1 repeating. What's 9? Oh, yeah, we're changing it up a little bit. So you spin the spinner shown 2 times. Each section of the spinner is the same size. Use this information to answer the question, giving a probability as a percent and rounding to the nearest 1/10 of a percent when necessary. Okay, question is, are the 2 spins independent? Yes. Unless you do something to make them not independent. So number 9. What is the probability that the spinner stops on 1 first and 2 second? All right, let's see. Well, we need to count. We need to count how many there are. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12. Now, how many ones are there? What is the probability that? So the probability of 1. How many ones are there? All right, we got 1, 2, 3, 4. I'm not seeing any others. So that's going to be 4 over 12, which is 1/3. Now, the probability of a 2 given a 1, which is really the same as the probability of a 2. Well, let's see how many 2s there are. 1, 2, 3. So 3 over 12, which is 1/4. What is the probability that the spinner stops on 1 first and the 2 second? That's going to be the probability of 2 intersection 1, which is the same as probability of 2 times the probability of 1. and that's going to be 1/3 times 1/4, which is 1/12. 1 divided by 12, that's 0.083, repeating, 0.808. Round to the nearest tenth of a percent. As a percent and rounding the nearest, so I guess that would, or 0.1, that's the nearest tenth. What is the probability that a spinner stops on 4 first and 3 second? So the probability of 4. Well, we got 1, 2 4s. So that's going to be 2/12, which is 1/6. And the probability of a 3 given 4. That's going to be the same as the probability of a 3. Well, how many 3s are there? Let's see, we got 1, 2, 1, 2. And that's going to be 1/6. 2 divided by 12 is 1/6. Probability of 4 times the probability of 3. 1/6 times 1/6 is 1/36. 1 divide 36. 0.027. 0.027, repeating. Number 11. What is the probability the spinner stops on an odd number at first and an even number second? So probability of an odd. And let's see here, let's go back here. How many odd numbers are there? Probability of an odd. 1, 2, 3, 4, 5, 6, 7. I'm counting 7. So we got 7/12. And then the probability of an even given odd. Well, if there's 7 odd, that means there are 5 even. Because remember, since this is with replacement, it's the same as the probability of an even number, which is 5/12. So we're going to end up with the probability of an odd times the probability of an even. 7/12 times 5/12. That's 35/144. 0.243. 0.243. 0.243. Was there? Yeah, I got it. All right. Good. What first number and what second number have the least probability of occurring together? What is that probability? All right, which one has the least on here? Looks like 5. 5. Yeah. 5. There's only one 5. Everything else has at least 2. So the probability of 5 on the first would be 1/12. And then the probability of a 5, given a 5, would be, again, since you put 1/12, since the two spins are independent. And so we're going to have probability of 5 times the probability of 5, 1/12 times 1/12. One over 40. Oh, that didn't. Yeah, 1/12 times 1/12. 1/44. 1/144.00. All right. Times. It's 1/144. And that's 0.0069. 0.0069. 13. Find the probability of getting a heads on every toss of a coin when the coin is tossed 3 times. Well, my question is, we got our first toss, we got our second toss, we got our third toss. What's the probability of getting heads on the first toss? Well, that's 1/2. What is the probability of getting heads on the second toss? Again, that is 1/2. Probability of heads on the third is 1/2. Multiply these and you get 1/8. Why? Because each one is independent unless you do something to make them not independent. You are randomly choosing cards one at a time with replacement from a standard deck of cards. Find the probability that you choose an ace, then a red card, and then a face card. So we have the probability of an ace. And we have the probability of a red card. And then we have the probability of a face card. So the probability of an ace is, well, how many of them are there? There are 4 aces and there's 52 cards total. Probability of a red card. Well, you have 2 red suits, 2 black suits. We have 26/52. Face cards, jacks, queens, and kings. Well, there are 4 jacks, 4 queens, and 4 kings. So that's going to be 12/52. If we multiply these, what do we get here? Control, divide. We got 4/52 times, and then control, divide. We said, what was it, 26? Yes, 26/52 times, and then we got one more, and that was the face cards. That's 12/52. 12/52, and that's 6/65. 6/65, and let's turn that into a percent. 0.09. 0.09. Okay, turn that into a decimal. All right, because 6/65 don't mean a whole lot. 0.09 might mean more. 15. Determine whether the given events are independent using the fact that the probability of A intersection B equals the probability of A times the probability of B, only when events A and B are independent. Okay. The manager of a produce stand wants to find out whether there is a connection between people who buy fresh vegetables and people who buy fresh fruit. The manager collects data on 200 randomly chosen shoppers as shown in a 2-way frequency table. Determine whether buying fresh vegetables and buying fresh fruit are independent events. Okay, Let's see what we got here. Well, bought vegetables, so that's probability of V for vegetables, and bought vegetables. $105 over 200. Let's see, 105 divided by 200. That's 21 over 40 equals 21 over 40. That's going to be hard to compare. So let's see here. 0.525. 0.525. Determine whether buying fresh vegetables and buying fresh fruit are independent events. So what's the probability of fruit? Let's see here. Bought fruit, I'm thinking 76 over, let's see that, 76 divided by 200. Well, how in the world did I get that? I got 76 over 200. 76 divided by 200. 19 over 50. 19 over 50. Maybe I need to show y'all how I got that. 76 over 200 equals 19 over 50. Okay. Well, what else do we got here? So we got the probability of fruit intersection vegetables. That's going to be the probability of vegetables times the probability of fruit. May have mixed those, but either way, we're going to have, well, 19 over 50, control, divide, that's 0.038, 0.38. So that's going to be 0.525 times 0.38. And that's, I get 1995 equals 0.1995 or 0.2. Okay. Now, let's do the probability of vegetables How did it want this done? We did that, but now okay. That's this right here. Now vegetables, intersection, fruit, where is that at? Bought vegetables, intersection fruit, let's see. Bought fruit, bought vegetables, that's going to be 56. That's 56 over 200. So 56 divided by 200. And that's 0.28 equals 0.28. Well, the probability of vegetables intersection fruit is not equal to the probability of vegetables times the probability of fruit. Now, why is this different than what we did earlier? Because they didn't put anything back, okay? And so these are not independent. Since the two are not, it is not independent. 16. The owner of a bookstore collects data about the reading preferences of 60 randomly chosen customers, as shown in a two-way frequency table. Determine whether being a female and preferring fiction are independent events. So we'll say FE for female, and we'll say fiction, we'll call that FI. Okay? All right. So the probability of female, well, there was 25 over 60, right? 25 divided by 60. 25 divided by 60, I get 5 over 12. 25 over 60, that's 5 over 12. And the probability of fiction, what do we got? Fiction, that's going to be 36 over 60, I believe. 36 divided by 60. And what was that? That was 3/5? Yes, 3/5. Okay. Now let's see. So we got the probability of being female times the probability of fiction, and that's going to be 5 over 12 times 3 over 5. The 5s will cancel. 3 goes to 12, 4. So I got 1/4 or 0.25. Now I got to do the probability of female intersection fiction. All right, female intersection, that's going to be 15 over 60. 15 over 60. 15 divide 60, and that's 1/4. All right. So now my statement is, since the probability of female intersection fiction equals the probability of female times the probability of fiction, the events are independent. The events are independent. "17. The psychology department at a college collects data about whether there is a relationship between a student's intended career and the student's like or dislike for solving puzzles." So determine whether planning for a career in a field involving math or science and a like for solving puzzles are independent. Boy, that sounds like we're going to do number 17 on the form. We're going to do number 17 on the form. Folks, you've been great. I appreciate you. We'll see you in class. Thank you.